So we can start, I think. Okay, hello everyone. So welcome to this afternoon session, and we're going to have a talk by Anke Kalauch from TU Dresden, Germany, giving us a talk on an order theoretical analysis of atomic JBW algebras. So there you go.
Thank you very much.
Oh, you're welcome.
You're the first one who pronounces my name right. Thank you. Yeah. Okay. Does it work? Yeah. Okay. So Amin gave me a difficult question. It's the fourth day of this very inspiring conference. He put me directly after the lunch to keep you awake after lunch. So yeah, I try my best. Please inform me if I don't succeed. Yeah. Pardon, Pedro? By snoring, yeah. Okay. Yeah, it's my pleasure today to be here, to talk here about a project that was originated 2017. There was a workshop in Leiden on 3 different topics. They invited people from order theory, they invited people from Jordan algebras, because Jordan algebras have a natural order, partial order. I will tell about this in a minute. And they invite people from metric geometry. And the plan was to see what is the intersection between these 3 topics and how the methods of one topic could interfere with the methods of other topics, etc. And yeah, then for Onno and me, this was a bit on the back burner, this topic. But unfortunately, Mark Roelands forced us to focus on this topic again and to see what order theoretical structures we can find in at least some class of Jordan algebras. So this is how this originated. I will give I will tell the first part of the story, and Onno will then tell the second part of the story after my talk. So people who know me a bit longer know that our approach is always, okay, learn from the people in lattice theory. Yeah, you all are from lattice theory, so most of you are from lattice theory, so you know all the nice techniques there. But there are many occasions where we still have a partial order, but not a lattice structure anymore. And what we want is to see how far can we go to take nice basic notions from the lattice theory, find generalizations of those, and investigate what happens if we still have a partial order that fits well to the vector space structure, but when we lose the lattice structure. Yeah, we play this game for many years now with Onno. And and it appeared that notions like disjointness, like bands, like ideals, all this we could do in partially ordered vector spaces. And then, yeah, we see where we want to see where there are applications, or how we can find all these structures in very natural objects, like today in kind of Jordan algebras. So this is a bit the story behind, and yeah, maybe. No. And the motivation for the things I want to talk about today is the classical Cadison theorem. So I will start with this, explaining a bit what structure we have in the B of H. And then yeah, establish all things I need for the more general case. So what the first part of my talk can be considered as a generalization of the classical Catteson's anti-lattice theorem. So what are you doing? Okay, I have to wait. It's okay. So let me remind you what we know about the nice space B of H, set of all self-adjoint operators in a complex Hilbert space H. One can introduce their Jordan product in the usual way. And the self-adjoint part of B of H is in this way a Jordan algebra. We lose the associativity, we get the commutativity, and we have an additional property for this product as written there. Moreover, we don't only have the Jordan product, we also have a norm. So with this, it becomes complete Jordan algebra, a GB algebra, and the norm has nice properties concerning the product and the norm are related in very nice ways. So we are in the structure of a GB algebra. Moreover, we have the identity operator, which gives us an algebraic unit in this Jordan algebra. And I said we have a natural order structure, and there are different ways to get the partial order there. One way is considering the spectrum of an element in the GB subalgebra that is generated by this element and our algebraic unit. And then we can consider classically the set of all elements with non-negative spectrum, and this gives a cone. Yeah. Equivalently, this cone is also obtained when we look at and as you know, if you have a cone, then we make partial order out of it by defining x less equal y when the difference is in the cone. And this partial order is compatible with the vector space operations. So we have in a very natural way a partially ordered vector space, B of H. So not only the algebraic structure, also the partial order there. But it's not the end of the story. Moreover, the operator I, the identity operator, is also an order unit. Yeah, so we can get every element in an order interval of minus lambda d unit and lambda d unit. And since we have Archimedeanity, we get the order unit norm. So the smallest lambda that fulfills this relation that I can catch the element in this order interval. So our B of H is in this way an order unit space. In brackets I wrote, it's also a previous space. I will explain in a minute what this means. So Catteson considered 1951 this partial order there and obtained even more, namely that it is not only partially ordered vector space, but even an anti-lattice. So here we are out of the nice oasis of lattice theory and end in the desert of partially ordered vector spaces. Yeah. And I hope that you follow me there. Maybe I should mention a partially ordered vector space is called an anti-lattice if two elements have a supremum if and only if they are comparable. No? There are no other elements who have a supremum. So NP of H, the self-adjoint part, is such an anti-lattice. And I like to show this very simple picture in R3, especially to lattice people. So we have different cones. What of these cones are lattice cones? Yeah, you know. These are cones of positive elements, yeah, of partial ordered vector spaces. So only in R3, when you have 3 extreme rays, then you have a lattice. When you have more extreme rays, you're out of the lattice theory. Yeah, when you're 4 or more extreme lattice, you're out of the lattice theory, and you end up in the ice cream cone, yeah, the circular cone, which is an anti-lattice. So there are no elements that have suprema. And so the world of partial ordered vectors is much bigger than the lattice world. And in the four-ray cone, this is in the middle. It's not a lattice, not an anti-lattice, because you have elements that possess a supremum when they are on the diagonals. Yeah, because the intersection of the upper bound is again the same cone, the same shape of a cone, so you have a smallest element. But there are other elements who don't have a supremum because the set of upper bounds is ugly. You don't find the smallest element. You see? So this is in between, no lattice, no anti-lattice. So now we are more in the anti-lattice world. So more, you can imagine these, for example, these spin factors, as we will call them, so these ice cream cones, yeah? This is typical for the anti-lattice world. So, as I told you, we want to look at notions that are well known in lattice theory and had to be introduced in the world of partially ordered vector spaces. So we start with disjointness. Everybody of you knows how disjointness is defined in a vector lattice, yeah? So the infimum of the moduli of the two elements should be 0. But we use an equivalent statement for disjoint elements, namely that the modulus of x plus y is the same as the modulus as x minus y. And if you have reduced any definition in the lattice world to something where only moduli are there, then we can translate it very easily into a definition in partially ordered vector spaces. And maybe I show you the picture first. Yeah, instead of taking the supremum of x and minus x for the modulus of x, we just take the set of upper bounds of x and minus x, yeah, to replace the modulus by this set. So any equation on moduli, we can translate into a relation of sets of upper bounds. So you can translate any definition, solidness and jointness and whatever. So let's go back. So that's what happens here. Yeah, instead of the modulus, I write just the set of upper bounds of x plus y minus x plus y, and on the right hand side the same for x minus y. This is the simple trick. So so the U means the set of upper bounds of these two sets, and if they are equal, then we say two elements are disjoint. So you could say, okay, is this definition useful? What is this good for? And so, but here I should mention, if you are in function spaces that do not have a lattice structure, like differentiable functions or something like this, this new definition gives exactly what you want, namely that two functions are disjoint when they have, if they have disjoint support. So this is a natural generalization of the standard disjointness in function spaces. So it's nothing weird about this, yeah? So this gives the properties you want. Okay, so we have disjointness now. And the question was, how is this disjointness related to well-known notions in the order theory, especially to anti-lattices? And together with Bas Lemmens from University of Kent, we could show that partially ordered vector space is an anti-lattice if and only if there are no positive disjoint elements. So it's a bit funny. Cattison claimed in his old paper of 51 that antilattices are as far away from lattices as possible. This is what he claimed in his paper. So what we were thinking at the first glance was that we will not find any disjointness in antilattices, yeah? But this is not true. You find disjoint element in antilattices with this generalized definition, but you don't find positive ones. And here, this is a point where the lattice world and the partially ordered vector space world is really different. Yeah. So in vector lattices, in your structures, every ideal is a sublattice, it's directed, everything is nice. Yeah. Bands are directed to order closed ideas, etc., etc. In partially ordered vector spaces, it can happen that these objects are not directed. So if I intersect them with the cone and take this intersection minus intersection, I don't end up in the ideal or in the band. So this one has to have in mind there is really a difference. And also here, there might be disjoint elements, but not necessarily positive. Also no positive elements in antilattices. So this is nice. So we have shown that this generalization of disjointness really has a close relation to this anti-lattice notion, the old one. So Cattison showed that there are that this is an anti-lattice, and one can even show a bit more. There are even no disjoint elements, also not non-positive ones. Yeah. So we call such partially ordered vector spaces disjointness-free antilattices. That's why we put disjointness-free. We add disjointness-free because yeah, it can happen in normal antilattices that there are disjoint elements, but in B of H not. And the other objects we will consider, it's the same. Yeah, we will not find disjointness at all. So back to our space B of H, as the self-joint part of it. It is a we have more structures, a JBW algebra. That means, shortly speaking, it's a dual space. And we need so-called atoms. So we look at all non-zero projections in JBW algebra, and a minimal element there is called an atom. And if every if you so to say take a projection and this dominates an atom, then we call this space atomic. And this B of H is an atomic JBW algebra. This is of this type. Oops. So the question is, what other objects are atomic JBW algebras? Let's look at this list. So B of H, the self-adjoint part I already mentioned. We can do the similar thing for quaternionic Hilbert spaces. We also take the self-adjoint part of B of HQ. This also turns out to be an atomic JBW algebras. The second point are the spin factors. These are generalizations of the ice cream cone I already mentioned. So we have a Hilbert space and introduce an appropriate multiplication there. And when we look at the cone of squares, we get something like the generalized ice cream cone. And third objects are the self-adjoint matrices with which entries from the octonions, 3 by 3 self-adjoint matrices. And we use the same product as we already introduced, the Jordan product. So all these are atomic JBW algebras, but the world is even nicer. This is more or less all you can get. This and algebraic direct sums of this. So this is a classical theorem that every atomic JBW algebra equals the algebraic direct sum of these 3 types of atomic JBW algebras. Those are called factors. So, and this motivated the project kind of. We wanted a theorem similar to the anti-lattice theorem of Keteson, but now for atomic JBW algebras. So that means one has to investigate all these different factors and see what happens there. So the plan was to find the structure, the order theoretical structure of these factors. So we have to find out whether there is disjointness or bands or whatever. And since every atomic JBW algebra is the direct sum of these objects, we have to see, so all these are order unit spaces. So what happens in order direct sum of order unit spaces? This is the second step. And if you have this, we can then go to disjoint sharing operators, etc., etc. Okay, that's the plan. Let's start with the first point. And the nice thing here is we get a result similar to the Keteson result, that all of these objects, all of these factors are in fact disjointness-free anti-lattices. Yeah, this is what we could obtain. I am going to hide all the technicalities here. I just want to show you the strategy, what one can do to obtain this result. So every of these factors is an order unit space, this we already discussed. Every order unit space has a so-called functional representation. I will explain in a minute. So what does it mean? You can embed an order unit space canonically into a space of continuous functions on a compact Hausdorff space. And the embedding needs nice properties. And if you have those, then disjointness translates from our order unit space to the functional representation. So this is nice because in the C of omega, I mean, you have functions, you can see what disjointness means. Yeah, it's pointwise disjointness there. So that's why we want to do this. So this is the third point. Disjointness in the order unit space is then equivalent to disjointness in the functional representation. Okay. So let me remind you quickly how this functional representation of order unit spaces is obtained. So we have the ordered unit norm I already mentioned. We go to the dual space X prime. We take there the dual cone and intersect the dual cone. So we take a basis of the dual cone. This is the sigma. Yeah, sigma is nothing else, but if you have a circular cone in mind, you just take the circle. You just take the intersection. So because the circular cone is self-dual, so you can go to the dual cone, which is also circular, and you take the intersection there. This is sigma. This is a base of the dual cone. And this base has nice properties. It's weakly star compact. So you can go to the extreme points by the Kronemann-Millmann theorem. Let's call the extreme points by lambda. Instead of all extreme points of sigma is this lambda. So this is then only the sphere left for the circular cone. Yeah. This lambda is in general not weakly star closed. So we take the closure there, and then it turns out lambda bar is then a compact Hausdorff space. So I can take this as the underlying space for my functional representation, and I embed my order unit space X in a canonical way. Yeah. And this embedding has nice properties. It's linear and maps U to the constant one function, and it turns out to be bipositive. All this is classical theory. Yeah, this is Keteson. So for us, it was of interest, is this embedding good enough? Yeah, in a way that we can translate it as disjointness. So there was some work to do. No, first I wrote it down for the spin factors. Yeah, here you see what sigma is, the base, and the lambdas, the extreme points. It's maybe not so spectacular. So just to show you how it works. we need a bit more of this embedding. And now I jump a little bit to the theory of prairie spaces, because those are spaces where we not only have a bipositive embedding, but we get even a bit more, namely order denseness. So we call a partially ordered vector space a prairie space if we have an ambient vector lattice. We embed into this vector lattice, and the image under the embedding is order dense in Y. That means every element in Y can be obtained as the infimum of elements of the small space above. One should remark here that this order denseness is quite a weak notion of denseness. For example, the polynomials of degree 2, maximum 2, are order dense in the continuous functions. Yeah, can make very narrow parabolas above and get the continuous function back. So finite dimensional space can be order dense in infinite dimensional space. Yeah, it's a weak order denseness. And if we have such an embedding, then we call the ambient vector lattice a vector lattice cover. And if we have such a situation, then we can deal easily with our new disjointness notion, because this translates one-to-one. But we need this order denseness, otherwise it doesn't work. And maybe a second remark here, this theory of prairie spaces, yeah, this popped up in 93 by a PhD thesis of Van Handel in Nijmegen with Van Roy as a supervisor. And the intrinsic definition of prairie spaces looks a bit artificial, but this is the essential thing, yeah, that we get this embedding theory. And please have in mind, every Archimedean directed partially ordered vector space is of this type, yeah? So when you are when you have in mind a closed cone, say in a Banach lattice or so, yeah, a closed cone, which is generating, so K minus K is the whole space, then you are already in the theory of prairie spaces. Yeah, so all interesting examples are of this type. It's not nothing weird or so. So most examples are.
That is in the sense of space, right?
Huh?
Then that orthogonality on the right.
Yes, of course, of course. On the left side, you have the new orthogonality, huh? In the order unit space or in the prairie space, and on the right hand side, you have the classical orthogonality in the vector lattice, of course, of course. Okay. So I said there was some work to do, namely to show that the classical Cadison functional representation theory fits into our scheme, that this space is in fact, so that this embedding is in fact an order dense embedding into the continuous functions on this lambda bar. Yeah, this was again work with Bas Lemmens some years ago. So by the classical functional representation of Cadison, we get in fact a vector lattice cover. And this makes the world nice, because now we can translate everything to this C of lambda bar space. And we have there pointwise disjointness, so there one can see what's going on. Okay, and with this trick, so now it's clear what to do. For all these factors I mentioned in the beginning, one has to do always a similar thing. Yeah, one has to look what is sigma, what is lambda, so what are the states? And this in the other terminology of the algebras, what are the states? And if I have this, I can see pointwise whether something is disjoint or not, and one can prove for all these three factors that there are no disjoint elements, yeah, at all. So that means all these factors in the representation of the atomic JBW algebras, all these factors behave similarly to the B of H case. Their disjointness does not exist there, which means first that they are antilattices, and second, they are even disjointness free in general. Yeah, and in this way, this is the theorem I wrote here. This is kind of the extension of the classical Cadison work, classical Cadison antilattice theory. So all of them are like this, and that means when I look for disjointness, in atomic JBW algebras, I have to look on these algebraic direct sums. This will be the next step. Okay, but first let me remind you what other order theoretic notions we have that might be of interest. So we have disjointness, so we can define disjoint complements in a canonical way. Then we steal the idea from Archimedean vector lattices. No? There you vector lattice people define bands as order closed ideals, but in Archimedean vector lattices it's the same as saying a set equals a double disjoint complement. Now in the partially ordered world, these two notions differ. So order closed ideals is not the same as this. So we use this notion here for bands. Yeah, a set that equals the double disjoint complements. And with this, we get also the notion of a projection band, namely then, we call it projection band projection if the range in the kernel are bands, and the range is then so-called projection band. And yeah, we more or less developed the theory of ideals and bands and all this, but we did not really consider projection bands. I don't know why. But then, there was this nice conference in Pretoria, and Jochen Glück was there, colleague from Wuppertal, young colleague, and he then very quickly proved all the nice things on projection bands we always wanted to know. Yeah, I just summarize it here in this proposition. So people were looking on these order projections that are between 0 and 1, and he showed that these are exactly the band projections. Yeah, so you can split the space in a band and it's double disjoint, and it's disjoint complement. And nicely, he showed that every projection band is in fact directed. So when you talk about projection bands, we are out of all these peculiarities of non-directed bands and so. So this problem we don't have there. So it was very, very quick. So this paper appeared within a few weeks or so. This was really nice and solved all questions we never asked before, but were kind of natural, yeah. And this helps here a lot. So we have to go to the second part. We have to put our attention to direct sums now of these disjointness-free antilattices. Yeah, so far we have all the factors as disjointness-free antilattices. Now the representation theorem of atomic JBW algebra says, okay, every atomic JBW algebra is in fact the direct sum of those factors. So let's investigate what happens there. Let's start simple. If we have two order unit spaces, we can look at the Cartesian product and get in a very natural way the functional representation of the Cartesian product of the two spaces. Here as a direct sum of the functional representations of the spaces on their own. And the nice thing is in number C that the spaces on its own are projection bands in the sense of Glück. So now we have to define what the order direct sum is of a collection of order unit spaces. This looks now a bit technical. The main point is that we have to deal with that it really stays bounded in a certain way. This has to be put in the definition. The cone is the natural one, the entry-wise cone. And we get an order unit in this order direct sum also in the canonical way. Yeah, I take the order unit in each of the order unit spaces. And we get the order unit norm there as well as a supremum of the norms in the components. So it's kind of a natural way to define this. And the nice thing is that the algebraic direct sum of JBW algebras is constructed exactly the same way. There you add the component-wise multiplication, but in fact, it's set-wise, it's the same construction. Yeah. So what was given in this representation theorem for atomic JBW algebras is exactly this order direct sum at the end. And if the all these phi i's are GBW algebras, then the direct sum is, and if they are atomic, then the direct sum is. So this translates everything. So everything is translated in a canonical way. If you have such an order direct sum of order unit spaces, then it happens as expected. Yeah, two elements are disjoint if they are disjoint in every of the coordinates. Yeah. So this is not really a surprise. And what comes out is more or less that these components in this order direct sum are projection bands with respect to this generalized disjointness. So we get projection bands there. Let's maybe take the next slide. So this is the summary of everything. If you have a collection of order unit spaces and you take the order direct sums, that whenever you can split the index set and they are indifferent, practically indifferent of these components. So with such structures, one can clarify disjointness easily. And for atomic GBW algebras, now we get this as a corollary, since in all the factors we have disjointness-free antilattices, so nothing happens within the factor, so only in different factors something essentially happens. Yeah, that only elements from different factors can be disjoint, and that's all. Yeah, so you have fully characterized disjointness in atomic GBW algebras. And if you have the disjointness, then you also have the bands. So this is only such divisions can be also such proper subsets of components can be bands. So this is the story about the order theoretical structures. There's Amin. Did you already fall asleep? There's still one little part left. Huh? Okay. So we have clarified all the part of also the structural part. And now I go back to a classical problem of the disjointness preserving operators. The definition is there. It's a natural one. You can define it in partially ordered vector spaces in a similar way now. And in the 19th, Huysmans, de Pacto, Koldunov investigated operators between Banach lattices and disjointness preserving operators there, and were asking, okay, if I have a disjointness preserving linear bijection, can I say something about the disjointness preserving inverse? And this is a long story. So there are many works of other colleagues as well. I just give the basic results here. In Banach lattices, it's nice, then the inverse is disjointness preserving. In vector lattices, it's not so nice. There is a counterexample given by Abramovich and Kittover. It need not be true in general. And we were wondering, how is this in Prairie spaces? Is there the inverse of a disjointness preserving bijection, disjointness preserving? And it was kind of a surprise. We didn't expect this, yeah, that in finite dimensions, everything works well. Yeah, that in finite dimensional Prairie spaces, the same result is practically true. And then we were kind of motivated also to look at more infinite dimensional settings. Just give some results in the similar spirit. And we could generalize up to a certain point, but this was difficult. This was not so clear whether this is true in general. Also, this we don't know until now, but some partial results. Let's put it like this: there were some partial results, and somehow it's clear that when we ask now the question for these atomic GBW algebras, is this true there or not? And here is an example that is not true in general. Yeah, take this very simple JBW algebra, a spin factor, direct sum of L2 and R, and then L infinity, and direct sum of those two, of spin factor and this L infinity. And the operator T steals the x1 from the spin factor and puts it into the sequence space L infinity. Yeah. And this operator is linear, of course, and disjoint is preserving. And the reason is kind of that here in the spin factor, we don't have disjointness. Yeah. So one can really calculate that this operator is disjoint is preserving. Let's look at the inverse. This operator S, this inverse of T, and here one sees this is not disjointness preserving anymore. So in general, we cannot expect such nice results as in the Banach lattice case. So we had to modify our question. Can we characterize those bijections, those disjointness preserving bijections that have a disjointness preserving inverse? This would be nice to have. And we can do it even with the whole setup I told you. We can even do it more general for disjointness, so for order direct sums of disjointness-free antilattices. Yeah, this is the right setup to ask this question. So the JBW algebras are only an example. Yeah. So, and in this setup, it turns out that those with disjointness preserving inverse, you just flip between the components. That's it. Yeah, practically. These are the only ones who have this property. Really, so we have a full characterization, and we can apply this to atomic JBW algebras. We get it as a corollary. Yeah. So what we learned from this project is really when we investigate these Jordan algebras from an order theoretical point of view, that the main object is in fact these disjointness-free antilattices. Yeah, and then we can apply everything to this algebra setup. So we consider the algebras kind of as a motivational example, so to say, to investigate these order direct sums. Okay, this was the first part of the story. So the whole business relies a lot on the books of Alfsen and Schulz and Hanche Olsen and Stürmer. And yeah, we have no clue how it works in GP algebras. Yeah, this would be the next question. What order theoretic notions appear there? This yeah, is an open question here. Good, this was the first part of the story.
Good. Okay, thank you. And if you have no name and we call you a horse, thank you for taking us through the desert. Does anyone have any questions?
Thank you for this talk. I'm not sleeping, but I am thinking about your denseness. You said that. No, because I think that I missed something, because you said that the polynomial of degree 2 are order dense in the set of function on set of continuous function on 0, 1. But what is order denseness for you?
In the sense, I should think of it.
Yeah.
So you have a continuous function, yeah? And order denseness means you look at all elements of the small space above. So you can take all parabolas here, yeah? You can take a point here and make them as narrow as you want with a little epsilon here. You can approximate this from above, you make the epsilon smaller. So, and then you take the infimum of all these parabolas and you end up with discontinuous functions. Yeah. So every element of the ambient vector lattice is the infimum of all elements of the small space above, practically. Okay. So it's a weak kind of denseness, as I mentioned. Okay. Chef?
I don't think so. Are there any more questions?
Thank you. Can we define the orthomorphism in partial?
Thank you for this question. So the question was, can we define automorphisms in our setup? Of course we can. Automorphisms are order-bounded band-preserving operators. We have bands. We can define band-preserving operators. And we all know that there is a very nice structure theory on automorphisms in the vector lattice case. Yeah. So we have the automorphisms, F algebras and all this. Yeah. And this is so. I mean, this playground of partially ordered vector spaces. Yeah. This is still. I would like to invite everybody to participate there, because we don't know much or almost nothing on band-preserving operators so far, and also not on automorphisms. Of course, there are so many natural questions there. Are these automorphisms again F algebra or has some structure like this? Janko, my PhD student, will give a talk later today. He will give some insights in this direction, some first little steps, but we are still in the beginning. Yeah, and the big problem here is that there's a broad range of partially ordered vector spaces. Now, on one hand, the lattices with many disjoint elements. On the other hand, the anti-lattices with no disjoint elements. And in between, there are different classes of partially ordered vector spaces. And for example, pervasive spaces who have many disjoint elements are not lattices, but also. And my feeling is that we have to search for results there where we have sufficiently many disjoint elements. Then we can ask these questions and see whether we get a nice theory or not. But yeah, this is an open problem. Thanks for this question. What?
Okay, is there anything else?
Thank you. Can you go to slide 32? I think it was, yeah, here, in the theorem here, should, when T goes from V to V, should that be from V to U? For V to W, I mean, because. In this, yeah, in the theorem, because here you say you have. So these are, but can you get a version where T goes from V to W? Yeah, well, let me formulate the question. Yeah. Oh, no, you can't answer yet. Because on the next slide as well, just it seems to me that this can be done for in the abstract sense, and on the slide 30, yeah, here it seems you should also be able to do it from one atomic to another. Now you have to repeat all of what you just said.
I repeat that Martin is right, of course, as always. And yes.
A good repeat. Any more questions? Okay, so I think you're using these enticing words like playground and invite us to come to. You're feeling lonely, aren't you?
I want to catch your inner child to join us.
Really, eh? You must come to the lattice world. Okay, well, let's thank our speaker. Thank you. And then we'll take a break until 3 o'clock and then have honor.
I have sorry. There is another question. Okay. There is another question here. Yeah. How does the theory transfer between real and complex GB algebra? This one. How does
Yeah, we don't know anything about. We don't have anything about GB algebras so far.
I don't know that
Let's see what he. Who is this?
someone from internet. So I invite him to open his mic.
No, or let him send the question to me by email also.
Okay.
Then
Oh.
this is easier. Then I can answer.
Okay.
Is he there?
Hmm?
Who is it?
He's Dimbi, but I don't know if he is Dimbi.
Did he open?
Yeah, it's open.
Hello?
Ah, he's not open.
No. Okay,
are
then.
open.
I'm open. So please send me an email. Then I can answer your
He's
question.
open.
Then I can answer your question by email. This would be the easiest way. Okay? Then we can discuss later.